Hello, my name is Pouya Hosseinzadeh, and to the following slides I'm going to present our works on improving the fault tolerance of convolutional neural networks through GAN-aided pruning, or in short GAP. In this line of research, we try to cease the transitioning process of faults into system failure, or in other words, reducing the STCs caused by activated faults into the system's memory elements. The common sources of faults are included as manufacturing defects, aging, high energy solar particle collision, or even reducing energy consumption by reducing the functioning voltage or refresh rate of DRAM memories. Silent data corruption are a kind of failures in the system that the total overall functioning of system does not halt, or the system does not restart, so the failure could not easily be found out. So the most intuitive metric to find out this kind of failure is accuracy degradation in neural networks. Two common faults which are studied in the literature are soft errors and hard errors. In soft errors, we could simulate that with bit Philip faults, which inflict temporal damage to the system. Bit Philips are a kind of fault which could be injected into the parameters of the network with changing a specific bit of parameters, and the hard errors inflict permanent damage to a specific part of memory and could be simulated by injecting Sedaghat faults into memory, which is persist memory value into 1 or 0, which are usually less of importance in compared to soft errors because they could be easily found and masked out. To evaluate the resiliency of our neural network, we conduct fault injection experiments, but for the low-level hardware libraries for FPGA or GPUs are not considered in our studies, and instead we use high-level application ones such as PyTorch FI and TensorFlow FI that are specifically designed for neural network researchers. Because our total implementation are done in PyTorch framework, we use PyTorch FI library. In the right side of the following picture, we could see multiple fault injection into a specific kernel or hypothetical kernel of neural network, and in the left side we could see a single bit Philip in just one weight of neural network in a specific kernel. There have been rich body of literature seek to improve the fault tolerance of neural networks, some of them done in hardware level and another are done in software level. In fault level training, researchers inject hardware characteristic of underlying hardware as optimizing information while network is being trained, and in fault level compression they do the same, but instead they use this information to compress or mask out insignificant modules of a system. In algorithm-based fault tolerance, they use the checksum technique in system memory to find out and mask corrupted memory elements. Until here, these introduced techniques are done in hardware level, and after that they are done in software or both software and hardware level. Range restriction are usually done in software level with optimizing proper bound for each layer output or activation function to in order to restrict the output of a layer and stop the output value to go beyond the specific threshold. In NAS technique, researchers optimizing specific architectures, reliable architectures for neural models in order to improve the model dependability. Recently, ensemble learning has been used to improve the fault tolerance of total AI-based embedded systems. Most of the introduced techniques are incur overhead into the system, or they reduce the capacity of neural networks and cause accuracy reduction. We propose GAP to mitigate these problems by reducing the complexity of convolutional neural networks while introducing a regularization to model parameters. We do so by using synthesized input to simulate the target domain statically before deployment stage, and to do so we take advantage of auxiliary tasks to inject these particular information to neural network parameters, that is norm values of gradient, to rank the parameters for pruning. We then evaluate the resiliency, as I mentioned before, with PyTorch framework, and at last we combine the three neural models just for sake of simplicity to compare between simple TMR and MVP version of these ensemble models. For pruning, we try different settings for structural and unstructured pruning. That is, former one is used to remove entire filter or kernel, and the latter is used to eliminate specific weights of channels. After our experiments, we find out that the best settings are a structural one that could bring most accuracy while have little accuracy degradation in compared to the most granular unstructured pruning. To encourage generalization to our model parameters, we use gradient information from the auxiliary task of synthesized data, and we remove out all elements that have higher norm, because the gradient norm show us that a specific weight should change in a specific direction that gradient shows in order to reduce the loss function. So the more the norm of gradient of an element, the less the amount of generalized an element could be able to bring to the model. To synthesize data, we use generative adversarial network, or in short GAN, to simulate the target domain, and we use conditional GAN in order to be able to use the labels of the data in later phases of our experiments. For auxiliary tasks, there would be usually another output head for the neural networks with the same data. For example, but in our experiments we try synthesize data as new input, and due to the fact that our loss function is the same categorical cross entropy, we could use the same output height for auxiliary and the main task. At last, we combine three differently prone neural network to compare the heterogeneity that emergent programming emergent programming that is design three or more differently prone or structured model into an overall learner. We could use comparison techniques such as quantization or pruning further to mitigate the overhead that extra models brings with themselves into the model. These pictures depict our schematic, the schematic view of our studies. In the first stage, we fine-tune the VGG network on CFARDEN dataset, and then train the CGAN while monitoring the generator, the synthesis data with the same VGG network to make sure that the quality of data is in a proper range of not being so good or too low of quality, and then calculate the gradient of VGG parameters on generated data, and after sorting the parameters regarding to their norms, we eliminate all the parameters with higher norms, and then we fine-tune the network on synthesized and training data, and after that with bit-flip fault injection campaigns we could make sure of resiliency of the model and test it. In this slide and in blue graph we could see that our model could significantly understand and detect vulnerable and insignificant weights in first layers of the model, that is alongside research in this area, in compared to their structure and unstructured pruning peers, and could significantly outperform with regard to the accuracy of the model. In this slide, we could see in the blue graph that our approach could outperform its other peer, especially in higher STC rates, that is of more important in compared to single bit flip faults, because harsh environments inflict and impact system in unpredicted manner that usually goes beyond just single bit flip in the model. For building up the emergent programming of our ensemble model, we combine three models with 10%, 15% and 25% of a structured threshold, and after conducting fault injection we could see that this MVP model could outperform its simple TMR structure pruning accuracy both in faulty and golden output. In this point my presentation is over, and it's up to me to thank my supervisors Dr. Harati and Dr. Yasser Sedaghat, and thank you for your attention.